All right, so time now for the big idea of the day. And the big idea of the day is the real exponential function. This is not as opposed to some fake exponential function. Ha 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 ha. This is about the exponential function that takes in real values. And as you know, there are far more real values than rational values. So we really do need to concern ourselves with the real exponential function. And to do that, we have a theorem. We're going to let alpha be a positive real number not equal to 1. And we're going to suppose that R and S are rational. Then, first, alpha to the R is positive. Hit the pause button. Think about why alpha to the R should be positive. Alpha to the R, well, R is rational. That's what that means. This has to be some positive number because alpha is positive and we're taking the qth root of it. And it's going to some, it's going to some integer power. So we raise a positive number to an integer power. This number must be greater than 0. So we are certain that that must be. If alpha is greater than 1, then alpha to the R is greater than 1 for all positive R. We should think about why that is true. Hit the pause button. Think about why that is true. Well, what do we know about alpha to the R? R is some rational number, so P and Q are integers, no common factors, Q is not 0. No common factors other than 1. Q is not 0. We know that alpha to the P has to be greater than 1 because alpha is greater than 1. And it's being raised to some integer power. So if a number greater than 1 is being raised to some power that's integer, then, right? We know that R is positive, so this is definitely a positive integer. So now we proceed by contradiction. We suppose that alpha to the P over Q is less than 1. It's easy to dismiss the case that alpha to the P over Q is equal to 1. So our contradiction will be with this. If that's the case, then this would have to be true, right? You take some number that's less than 1, you raise it to an integer power that remains less than 1, but this implies that alpha to the P is less than 1, and that's your contradiction. So if alpha is greater than 1, then alpha to the R is greater than 1 for all positive R values. You take reciprocals and you get the case where alpha is between 0 and 1, no problem. Time now for the third result. The third big result says if alpha is greater than 1 and R is less than S, then alpha to the r is less than alpha to the s. That is, alpha to the x is increasing on the rational numbers when alpha is greater than 1. And that is a key result. Alpha to the x, the exponential function, is increasing for the rationals. So how do we establish that? Well, we take a look at what alpha to the s minus r is. So alpha to the s minus r is alpha to the s over alpha to the r. But we know that r is less than s, which means that this is a positive number. And because this is a positive number, this says that that's greater than 1. And that implies that alpha to the s is greater than alpha to the r as needed. So what? Let alpha be some positive real number, and let x be a real number. Then here's what we say. Alpha to the x is the limit as n approaches infinity of alpha to the r sub n, where the sequence r sub n is a sequence of rational numbers that converges to x. In the same way that we defined every real number as a Cauchy sequence of rational numbers that converges to that x, we are going to define alpha to the x as the limit of a sequence where we generate x by taking a sequence of rational numbers that converges to x. With this definition, the following are true. 1. The range of the exponential function is the positive real numbers. If alpha is greater than 1 and the exponents are positive, then we generate everything greater than 1. And we can take reciprocals and get everything between 0 and 1. The exponential function is increasing if alpha is greater than 1 and decreasing if alpha is less than 1. The exponential function is 1-to-1, and all of your real analysis work is going to establish that if a function is monotonically increasing or monotonically decreasing, then the function is 1-to-1. If you take alpha to the gamma times alpha to the sigma, that's alpha to the gamma times sigma. That's, gamma plus sigma. Yes, I know exponents. Sure I do. If you take alpha to the gamma and raise it to the sigma, those exponents multiply. And of some importance, and we'll prove it next time, the exponential function is continuous on the real numbers. We need a couple of things in place before we can get there. That's the big result for Thursday. The big result for Thursday gets us to a place where we can recognize that the exponential function is continuous for all real numbers. That's comforting because we treat it like it is. And if we treat it like it is, it probably ought to be. We will verify that when we gather on Thursday. On Thursday, there will be two videos. One of them is going to establish sort of, kind of, with a minimal amount of hand waving, that the exponential function is well defined, and then the other one will work toward establishing that the exponential function is continuous. Okay, that's about enough for now. Go do something else other than this. We'll see you next time.